Hey everybody, in this video I'm going to be going over example 16.3 from your textbook with you because this example is pretty complicated and I feel like it would be helpful to go over it a second time, especially like with another person, because it is a pretty long and complicated example, but also pretty important. And if you can understand this example, you're really setting yourself up for success in future problems like this. So let's jump right into it. Example 16.3, part A. We are given a buffer solution that is 1 molar acetic acid and 1 molar sodium acetate. And we are asked to determine the pH. Now, whenever we are asked to determine the pH, we know that we have to find the hydrogen ion concentration. And in order to do that, we need to set up some ice tables. The first table that we're going to set up is with this sodium acetate here, because we know that sodium acetate is a salt. So what do we know about salts? We know that salts will completely dissociate in water into ions. And because it completely associates, this is not going to be an ice table, but an ICF table. Our starting concentrations are 1 molar for our sodium acetate and 0 for our ions. Our change is we're going to lose one of these and gain one of each of these. And because it completely dissociates, we know that our final concentration is going to be 0. And therefore we can look at this and say our X is going to be 1. So we can put 1 for our final concentrations of both of these ions. And the reason we did this first is because this ion is going to be involved in the ice table with our acetic acid. I'll show you guys what I mean. So now we are going to set up our ice table for acetic acid. CH3COOH is in equilibrium because it's a weak acid with hydrogen ions and our acetate ions, right? And it's in equilibrium, so it's going to be an ice table. Our initial for this is going to be 1. Our initial hydrogen ions are 0, and our initial acetate ions is going to be 1, carried over from the 1 we determined here. So this will get plugged in there. And then our change is pretty much the same thing we've always been doing, where we are losing one of these, gaining one of these, and one of these. So our final concentrations are going to be 1 minus X, X, and 1 plus X. Okay? And now what we need to do is we need to look at our Ka. Our Ka for acetic acid can be found in table 15.3 from your book. That's where you're going to find a lot of these Ka constants. So from this table, our Ka of acetic acid is 1.8 times 10 to the negative 5. Okay? And then we can take our Ka and write the expression that Ka is equal to products over reactants using the information from this ice table. So we can say 1.8 times 10 to the negative 5th is equal to the concentration of our reactant, or our products over the concentration of our reactants. So our hydrogen ions are X, our acetate ions are 1 plus X, but we are going to make the assumption that X is negligible. So we can say that this is just 1. And then our final on the bottom is just going to be 1 because we're going to make the same assumption that X is negligible. Right? And then you multiply this out and we can pretty easily see that X is equal to 1.8 times 10 to the negative 5th. And that's great because that's what our hydrogen ion concentration is X. So we can say that this is also equal to our hydrogen ion concentration. And now that we know our hydrogen ion concentration, we can pretty easily solve for pH, because pH is the negative log of our hydrogen ions. And so if we plug in negative log of our 1.8 times 10 to the negative 5th, we get a pH of 4.74, which makes sense because this is an acidic pH and this is a weak acid. So that makes sense, right? And that's our part A. Let's move on to part B, where we start to mess with our buffer a little bit. So part B says that we have our buffer solution, and to that we add 0.1 moles of hydrochloric acid gas. So the volume doesn't change, to 1 liter of our buffer. And we want to know what is the new pH. Basically, we want to know, is our buffer effective at being a buffer and maintaining a stable pH when acidic or basic substances are added? So let's start off part B by writing an ICF table for hydrochloric acid. We know it's not an ICE table, it's an ICF, because hydrochloric acid is one of our 6 strong acids, which mean it will completely dissociate into hydrogen ions and chloride ions. All right, so let's just go ahead and fill it in. We start with 0.100. We lose X here and we gain X here and here. And our final is 0 because it's a strong acid, it completely dissociates. So we can look at this and we can say that X is 0.1. And we can take that and plug it in here. Okay? So now we can look at this. We have our hydrogen ion concentration. These hydrogen ions will react with our buffer that we have in part A. So what we need to do now is think, what will this hydrogen react with from our buffer? And we look up here and we say our hydrogen will react with this ion, this acetate anion. And so now we need to write another ICF table of some of these anions from up here reacting with our new hydrogen ion that we produced from the hydrochloric acid to react and form our acetic acid. Okay? So for starting off here, our initial concentration of this is 1, based on what we did here, assuming that X is negligible. Our initial concentration of hydrogen ions is 0.1 from here. And our initial concentration of our acetic acid is also going to be 1 from our previous ICE table. And then our change, we're going to lose X, and gain X. And then if we multiply this out, we know that our final hydrogen ion concentration is going to be 0. Because this is an ICF table, this is going to be 0, so we can now back calculate, and we know that X is going to be equal to 0.1. So if we plug that in here and here, 1 minus 0.1 is going to be 0.9, and 1 plus 0.1 is going to be 1.1. And your textbook notes that X is 0.1. Your textbook notes that this ICF table is in moles. It doesn't really affect the problem too much because all of our concentrations are very basic. Like we have 1 and 1, so if you were to convert that to moles, it really wouldn't make any difference, but it's a good thing to keep in mind when you're looking at the textbook's example. All right, so now what we need to do is to make another ice table. There's a lot of ice tables going on in this example. This time we are going to take our acetic acid from here and write an equilibrium equation with our hydrogen ions and our acetate anions. Essentially the same ice table that we did up here, but accounting for the differences that our new hydrogen ions have brought to the table. So this is going to be an ice table. Our initial concentration, oops, I forgot an O in there. Our initial concentration of this is going to be our 1.1 that we got right here. Our initial concentration of hydrogen ions is 0, and our initial concentration of acetate ions is going to be 0.9 from here. Our change, we are losing X here, gaining and gaining. And our final, we are going to say that this is 1.1 minus X, X, and 0.9 plus X. Here we need to make some assumptions, the same assumptions that we made up here, in that we are approximating that X is negligible when we are writing our equation. We're going to use our Ka again. Because this is the same table, we use the same Ka. So we can say that 1.8 times 10 to the negative fifth is going to be equal to our products over our reactants. In this case, we have X for our hydrogen. Our assumption is that this is negligible, so we're just going to call this 0.9 and the whole thing over, making the assumption that X is negligible, 1.1. And if you plug this into your calculator, you find out that X is now equal to 22 times 10 to the negative fifth, which is helpful because that is what our hydrogen ion concentration is. So now we can take that new hydrogen ion concentration and plug it into our pH formula, the negative log of 22 times 10 to the negative fifth. Calculate that out and we get a new pH of 4.66, which makes sense because our old first pH before the addition of acid was 4.74. Now it is 4.66. It has gotten slightly more acidic with the addition of hydrochloric acid, but it has remained relatively stable, demonstrating the purpose of a buffer solution. I hope this helped. I know this example is pretty long and complicated. It's really good if you're able to understand this thoroughly, and I hope this video helped you get through it for the second time. Reach out with any questions because this is pretty complicated stuff, and you can check out anything else I have posted on Canvas too.